All right, so today we're going to talk about speed and velocity. Now, we've probably heard the term speed and velocity. Maybe we've used them in our everyday lives, but do we truly know the difference between speed and velocity? So, in order to know the difference between the two, we need to remember those terms scalar and vector. Okay, we talked about scalar and vector already, and we said that scalar was just magnitude. Okay, it's just a number, it's just a value. Vectors, however, have magnitude plus direction. Okay, so that's what makes vector a little more important. Okay, it tells us a number, it tells us a value, and it tells us where something may be going. Okay, so we need to remember those terms when we're thinking speed and velocity. Okay, our first term, speed. Speed simply, in its simplest definition, says that it's the distance an object travels per unit time. Okay, in other words, it's how far something travels and how long does it take to get there. Okay, we can also refer to it as a rate of change in distance. Okay, our distance is changing as time continues passing by. Now, down here at the bottom, we can represent that in an equation form simply as speed equals distance divided by time. And even simpler as S equals D over T, where S equals speed, D represents distance, and T represents time. Now, this is going to be very important. We're going to use this moving forward. S equals D divided by T. Velocity, on the other hand, is speed with direction. So speed was really just a number, it's just a value. But once we add direction to that speed, we are now velocity. We're now a little bit more important. We have not only just a number, but we know where we're headed. We have a direction attached to it. Okay? So we can say that velocity is a vector. Velocity is a vector because it has that direction associated with it. Now, velocity can be fast, it can be slow, just like speed is, except that direction is added to it. It can also be moving up or down, left or right. Now, last week we talked about how negatives give us direction. They indicate direction. So one way I want you to think about this is if you have your number line, and let's say this is 0. As you go to the right, your numbers are all positive. As you go to the left, your numbers are all negative. Okay, if I'm on a coordinate plane, and this is my y-axis, this is my origin, if I go up my y-axis, my numbers are positive. And if I go down my y-axis, my numbers are negative. So the positives and negatives indicate that direction. And it'll be very important that we indicate that. Otherwise, we don't know where we're going. Okay, so movement to the right or up is a positive value. And movement to left or down will be considered negative. Okay? Now, there are a couple types of speed. Speed that does not change over time is what we call, is what we call constant speed. Okay, constant. That word constant means not changing. It stays the same. So if speed is constant, that means it's not changing over time. Okay, it doesn't change. Now, it's not typical that we have constant speed or witness constant speed in our everyday lives, but it happens. Okay, a lot of times we're pressing on the gas to move in traffic. We're stepping on the brake to come to a stop sign. You're walking fast in the hall because you're running late for class. Whatever the reason, we typically don't see a constant speed, but speed that doesn't change is referred to as constant. Now, two other types of speed. We have what we call average speed, and the average speed is just the total overall distance divided by the total time. Okay, and it's still d divided by t, just like our first equation. Instantaneous speed is how fast you're going at any particular point. So if you're along a road trip, if I ask you at one specific time how fast are you going, that is your instantaneous speed. It's not an overall average, it's just your speed at that moment. Okay, so here's our speed equation, our average speed equation, and it looks just like our original speed equation. You still have your average speed divided by the speed equals distance divided by time. Okay, that has not changed. It's still S equals D divided by T. Distance traveled divided by the time it took to travel that distance. Velocity is a little bit different because remember, velocity is a vector, and velocity is the total displacement divided by the time. Okay, displacement is a change in position. So a lot of times you'll see this velocity equation written as V equals delta D, which represents a change in distance. It's a change in position. It's representing displacement, all divided by T. So essentially all you have here is V equals D over T, displacement divided by time. Okay, it looks very similar to our speed equation, except one has direction, one does not. Okay, now a couple things I want you to think about. Can you have a negative speed? Well, if speed is just a value, it's just a number, we can't attach a negative to it because the negative indicates direction. Okay, so scalar quantities, because speed is scalar, you cannot attach a negative to it because a negative gives us direction. Can you have a negative velocity? Certainly, because velocity is a vector and negatives give us direction. Velocity can have a negative associated with it. You can have a negative 4 meters per second. That doesn't mean that you're slowing down. That means that you're either moving to the left or moving to the right. Okay, is distance a vector or scalar? Distance is just magnitude, therefore it is scalar. And displacement is always in reference to a starting point, so therefore it has direction, it becomes a vector. Now, our first example says, while on vacation, Lisa traveled a total distance of 440 miles. Her trip took 8 hours. What was her average speed? Okay, so in order to do this, you need to know your speed equation. And that speed equation is given to you right here. Speed equals distance divided by time. Now remember, we can simplify that and abbreviate it. S equals D divided by T. Speed equals distance divided by time. So what we want to know in this problem, we can identify that we want to know her average speed. So we don't know what S is. Okay, so S is unknown. Then it says at the top, she traveled a total distance of 440 miles. Okay, so this distance is D. She traveled 440 miles. So D is 440. And how long did it take her to travel that distance? It took 8 hours. Okay, so our time is 8 hours. So now we've identified what we need to solve for. We've identified what is given to us in the problem. We know distance, we know time. Now we can take these variables and plug them into our equation. So we're still talking about S. Our distance is 440. Our time was 8 hours. And when you divide 440 by 8, you get 55 miles per hour. So she was traveling 55 miles per hour on average. Okay. Now this scenario describes a person traveling 100 kilometers from city A to B. The first half was driven at 50 kilometers per hour. The second half was driven at 100 kilometers per hour. What was her average velocity of the trip? So I see some information in here. I see that it's asking me what her average velocity for the trip was. All right, so in this case, our velocity is unknown. I also see that the car traveled 100 kilometers from city A to B. So they're traveling 100 kilometers from city A to B. So this is giving me my displacement. This is my delta D. This is my displacement. Now it tells us that the first half of the distance is driven at 50 kilometers per hour. The second half is driven at 100 kilometers per hour. Okay? So if we take that into account, we know that the first half of the trip took 1 hour because she was only traveling 50 kilometers at 50 kilometers per hour. So that took her 1 hour. The second half of the trip took half an hour because she was speeding up. She doubled her velocity. She was going 100 kilometers per hour. So she reached that second half in half the time. So if we use our velocity equation, which is V equals displacement over time, we know our displacement was 100 because she traveled 100 total kilometers. And in total, it took her 1.5 hours. Okay? And when you divide 100 by 1.5, you get 67 kilometers per hour, roughly. We rounded up to the nearest whole number there. Okay, in our next example, we have a diagram here, and we want to compare the distance to the displacement. Remember, distance was the total length traveled. Displacement was that shortest path back to where we started. If we could draw one straight line back to where we started, that would give us our displacement. Okay, so if I want to know the distance, I can simply come over here and take 0.4 and add 0.3 and add 0.4. And when I add those three together, you get 1.1 kilometers. 0.4 plus 0.3 plus 0.4 gives you 1.1. Now, our displacement isn't as easy as saying, well, if I go back the same way, I'll get 1.1 kilometers. Remember, our displacement is the shortest pathway back to where we started. If I can draw one straight line from the school back home, that gives me my displacement. Okay, so for this one, you're going to have to think a little bit outside the box. If I extend this out here and extend this down here, and that straight line from school to home is here, you notice that we formed a triangle, a right triangle. Okay, now for this, you're going to need to use Pythagorean theorem to calculate that side. Okay, now if this side right here is 0.4 kilometers, that means that this little side right here is also 0.4 kilometers. And if this side right here is 0.3 kilometers, then that means that this side here is also 0.3 kilometers. Okay, now it comes down to solving for our hypotenuse. Okay, I know this total side is a combination of 0.4 and 0.4, so that gives us 0.8. This side is 0.3, and we want to solve for this unknown side. So you set up your Pythagorean theorem, which is a squared plus b squared equals c squared. Where side A, we're going to call this side A. If I add up 0.4 and 0.4, side A now becomes 0.8 squared plus side B, we'll call this side B, is 0.3 squared equals C squared. Now, you can type this into the calculator. We'll call this A, B, C. You can type in this into the calculator. You can square 0.8, you can square 0.3, and then take this final overall square root, and you'll notice that your displacement should come out to 0.85. 0.85 kilometers, and our distance was 1.1 kilometers. So a lot of times our displacement is going to be either the same as our distance or significantly shorter because you're taking that shortcut, that straight path back to where you started. Okay, so now we're looking at differences between speed, and in the next slide we'll look at velocity. So remember that speed was distance divided by time. Okay? Now, speed is what we need to solve for. Distance, we already solved for on the previous slide. We said that our distance was 1.1 kilometers. And the time it took to reach 1.1 kilometers was 5 minutes. Now, normally we would convert minutes to seconds, but for the sake of the notes here, we're going to leave it in minutes. Okay, so we have a distance of 1.1, a time of 5 minutes. We need to solve for speed. So what I'm going to do is I've already found what I know and what I don't know. I'm going to substitute and solve. So I'm solving for S. So I'm going to leave S over here. I need to fill in my value for D, and D was 1.1 divided by T, we said was 5. And when you divide 1.1 by 5, you get 0.22 kilometers per minute. Now, normally we won't leave things in kilometers per minute, but for the sake of the notes, we will. 0.22 kilometers per minute. That's roughly 3.5, almost 4 meters per second. Now we're looking at same scenario, but velocity. Okay, we want to know the average velocity. So it's very similar to our speed equation, with the exception that velocity has direction. So instead of dividing our distance by time, we're dividing displacement by time. Okay, so we still want to know V. V is unknown. Displacement we solved for on the previous 2 slides ago, and we said that our displacement was 0.85 kilometers, and our time is still 5 minutes, and we'll leave it in minutes for the sake of this. So I've identified everything that is given to me. I know what I'm trying to solve for. Now I can simply plug it into my equation. Okay, V is what I'm ultimately solving for, so I'm going to leave it over here, and then over here I'm just going to substitute everything that I know. I know my displacement was 0.85 divided by, I know my time was 5 minutes. And when I divide 0.85 by 5, I get 0.17 kilometers per minute. 0.17. Now, again, we probably will never leave things in kilometers per minute. We'll get into conversions later on, but for now, for the sake of the notes, we'll leave it in kilometers per minute. 0.17. That's roughly, it's almost 2.5, 3 meters per second. Okay, we're going to talk briefly about acceleration. We're not going to talk a whole lot about it this we'll get into it in more detail next unit, but I do want to mention it. The simple definition of acceleration is that an object's rate of change of velocity. So if the velocity changes, then we have acceleration. If we speed up, if we slow down, or we change our direction, we're changing our velocity and therefore accelerating. Okay, so these three keys will identify something or an object that is accelerating. If you speed up, if you slow down, if you change direction. Okay, now if you think about this in your car, if you've ever driven before or seen someone drive, there are controls in your car that allow you to speed up, slow down, or change direction. If you were to speed up, you would press on the gas pedal. If you were to slow down, you're going to hit the brake. And if you were to change direction, you would turn the steering wheel. Okay. Now, I can't tell, maybe it's the PowerPoint slide or it's not transferring right, but this is one heck of an equation. Okay, what that equation should say is that your acceleration equals a change in velocity divided by time. Remember, as our velocity changes, we accelerate, and we can measure that by dividing it by time. It's the rate of change of velocity. Now, if I break this down a little bit further, and it's going to get a little crunched in here, A is our change in velocity. Okay, we have a starting velocity, we have an ending velocity. We could represent that as a final velocity minus our initial velocity, all divided by time. Okay, this is the equation that we are going to use most when solving for acceleration, or the acceleration of an object. Acceleration A is equal to a change in velocity. So it's final velocity minus our initial velocity. We're speeding up or we're slowing down, whatever it may be. There is a change occurring. Okay, so final velocity minus initial velocity, all divided by time. It's still a rate. It's still a rate. Okay. Now, a couple images here that can help you understand. If you are looking at this first tape up here, okay, you see that the dots are evenly spaced. There's a pretty good gap between each. Okay, so if you imagine these were footsteps and you're walking across the room, you're taking big steps across that room. Okay, so chances are you're moving pretty fast across the floor. When you look down here, if you imagine these as footsteps, okay, you're taking baby steps, one step right in front of the other. You're moving pretty slow. Unless you have giant feet, you're moving pretty slow because these steps are tiny. The space in between here is very minimal. Okay, these are baby steps. This is something that is moving slow. But if you notice, the spacing between each appears to be the same. Same up here. The spacing between each appears to be the same distance. So these look like they might be moving at a constant rate. They're not speeding up, they're not slowing down, they're staying the same.